In this research paper titled Transformers for Complex Query Answering over Knowledge Hypergraphs, the authors, Hongting Sang, Zihao Wang, and Yangchu Song from the Hong Kong University of Science and Technology, address the challenges of handling complex queries on knowledge graphs that go beyond simple binary relationships. Knowledge graphs, or KGs, are structures that represent facts as triplets, consisting of a head entity, a relation, and a tail entity. For example, a triplet might look like Albert Einstein, born in Germany. These graphs have been widely used to model real-world data, but they operate under the open-world assumption, meaning they are often incomplete and require methods to infer missing information. The paper highlights that while traditional KGs work well for binary relations, they struggle with more sophisticated real-world facts that involve multiple entities or varying levels of complexity. To overcome this, the authors introduce the concept of knowledge hypergraphs, or KHGs, which can handle n-ary relations, meaning relationships involving more than two entities where all participants have equal importance. For instance, consider a relation like co-author, involving three authors, author A, author B, and author C in a hypergraph. This can be represented as a single hyperedge connecting all three, preserving their equal contributions. This is different from hyper-relational graphs, which might break it down into triples with additional qualifiers, potentially losing some nuance. The core focus of the paper is on complex query answering, or CQA, which involves using logical operations to query these graphs. CQA is crucial for tasks in neural graph databases, where users perform queries with operators like projection, negation, conjunction, and disjunction to find answers in incomplete graphs. The authors point out that most existing CQA methods are designed for standard KGs and don't fully address hypergraphs. They review previous approaches, such as embedding models that represent entities and relations as vectors in a space, and methods like CQD and LMPNN, which use pre-trained embeddings and message passing to handle existential first-order queries with a single variable, known as EFO1 queries. However, these methods fall short for hypergraphs. To fill this gap, the paper introduces two new datasets, JF17KHCQA and MFB15KHCQA. These datasets are sampled to include a variety of query types that incorporate logical operations. JF17KHCQA is based on the JF17K dataset, while MFB15KHCQA builds on MFB15K, both adapted for Hypergraph CQA. These datasets allow for testing queries that involve projection, which extracts specific variables, negation, which excludes certain results, conjunction, which combines conditions with and disjunction, which combines them with or. To tackle CQA on these knowledge hypergraphs, the authors propose a novel model called the Logical Knowledge Hypergraph Transformer, or LKHGT. This is a two-stage transformer-based model designed specifically for reasoning over hypergraphs. The first stage involves the projection encoder, which handles atomic projections. This means it focuses on predicting answers for variables within simple hyperedges. For example, if you have a hyperedge representing a multi-entity relation, the projection encoder processes it to identify potential answers for a given query variable. The second stage is the logical encoder, which manages more complex logical operations. Together, these encoders enable the model to process existential first-order queries on hypergraphs by breaking them down into manageable parts. Both encoders incorporate a feature called type-aware bias, or TAB, which helps in capturing interactions between tokens based on their types, such as entities, relations, or logical operators. This bias mechanism ensures that the model pays attention to the specific roles of different elements in the hypergraph, improving accuracy in query answering. The paper emphasizes that LKHGT is designed to generalize well, even to out-of-distribution query types, meaning queries that differ from those seen during training. Experimental results on the new CQA datasets demonstrate that LKHGT outperforms existing methods, achieving state-of-the-art performance for CQA over knowledge hypergraphs. In their experiments, the authors show how LKHGT handles the limitations of previous models by effectively dealing with n-ary relations and complex logical structures. For instance, While models like StarQE focus on hyper-relational graphs with qualified triples, LKHGT directly addresses true hypergraphs, making it more versatile for real-world applications. Overall, this work extends the capabilities of transformer models from natural language processing to graph reasoning, paving the way for more advanced query answering in incomplete and complex knowledge structures. The author's contributions lie in creating new datasets, proposing an innovative architecture, and demonstrating empirical success, which could influence future developments in knowledge representation and artificial intelligence.